Okay, thank you. I guess it's time to get to the next speaker, which is Ralf Jaumann and the Dawn Science team. The talk is about the geomorphology and topography of the interior of Occator crater on Ceres.
Okay, yeah, I'm coming to a little bit larger environment of this central pits and look into the interior of this Occator crater. It's the most impressive feature on the surface of Ceres, and as you see, it's a very large crater. We have about 100 kilometers, close to 100 kilometers diameter. We were able to do a very good topographic map of this impact crater, which gets to the requirements the Dawn mission has. So that means a tenth of a pixel height resolution, and we got the tenth of a pixel height resolution. Basically, it means with an accuracy of about 1.5 meter accuracy. The total height is about 7.7 kilometers. So we have a very high rim area, and we have a very deep area in this central pit. Okay, if you look a little bit closer at this, there is also some kind of spectral variations within there. I don't talk about the spectral variations, but it's completely clear that we have different materials. The crater rims show in the visible some kind of a reddish characteristic. The floor, or parts of the floor, show a bluish characteristic, and then we have the bright material of the central pits. Okay, yeah, if we make a very rough map, then we can clearly see that's the topographic map, that's the topographic height. So we can clearly see that we have some kind of mass wasting features which are coming from the rim area, and then we have some kind of inner part, which is some crater filling. And we can see in all going this border, we can really see that this material has been ponded against the mass wasting material. So there are two different directions of emplacement. Okay, that's one area where we can see the mass wasting material, which is coming down from the crater rim, and then we see the material which is here, the inner part. So that's still the height, so red is high, blue is low area, and we see a lot of tectonics here also. I will come to this later. Then if we look into the interior part of this, then we see material which flow features which are going in this direction, mostly in this direction, and we see a lot of ponding in this area. If we look a little bit closer, we really can see that flow features which are going to this feature, which is coming from the crater rim, so the flow has been really ponded here. And we were able to do a very high resolution topographic map out of this, so that shows the contour lines about with a 50 meter equidistance, and using profiles or cross sections out of this, we really can see that there is two parts in this crater. If we go this section here and also go this section here, but here you can see it from C to D. This part of the impact crater, which goes until the pit area, is much higher than the area where we have the filling in this material. And there are a number of ideas behind this. So the difference between this is we are 500 meters high here, and we are below minus 500 meters here. Probably we have some kind of subsidence of the crater floor. That's one of the ideas, and means at least we have something which has some place to fill in material, or we have some kind of fill in material which has been evaporated and lost its volatiles. So that's the two ideas which can be behind this difference in the crater floor height. One is to really have some kind of infilling in a broken area in this part of the crater, or we have impact melt here, which was very volatile rich, and after evaporation, so the material which has been shrinked to the volume which we see today. Okay, if we look in another direction, that's this way, then we really see we have impact melt or whatever this plane materials in the interior is, but we see it's both on both sides of the central pit and the central dome. Okay, and if we look a little bit closer into this material from the topography in this plains and flow material, and we look at this area where we have some kind of a flow front here, and look into this flow front at the highest resolution of topography we have, we really can see that this flow front, that this flow front has at least a height of 300 meters in this part, from the lowest part here to up of here. So it's a really significant flow which appears here. And that's the other one I already showed, which points against the mass wasting deposits from the crater rim. And this flow has about 150 meter, is about 150 meter high. And if you look at this here, it has a very points against this very steep slope here. Okay, so that gives us a plains material thickness of about 700 meters in this whole area. And if you take the area and the thickness we have here, then we get plains material which is in the order of 3,300 square cubic kilometers. So that's a lot of material, and the next step here will be to really look into whatever material this is, how long it needs in order to, let's say, solidify this material within the impact crater once it has been liquid. Okay, if we look at the distribution of the direction of the flow fronts and the direction of the mass wasting, then we really can see most of the flows which can be identified are coming from the inner area. So they are going in some kind. Here we can really see it going in this direction, and probably there are some flows more flow-like than the mass wasting features which are coming back from this kind of area, which is the deepest area in the crater. And then if you look at the topography of the inner part, that means of the bright material, which are exposed in two parts. That's the central pit and the central dome. We already heard about a lot of this, and there is another area, Vinalia, which also shows bright material. And if we start to look into the topography, then we really see that the central pit above the base has about 700 meters, and the surrounding is relatively high, so that this one massif is about 1,000 meters above the base, the deepest point of the pit, and this area is 2,000 meters above this, and there are some other remnants which are again 1,000 meters. So there is some kind of, let's say, strong material which is around this pitted area, and this strong material seems to be some kind of a remnant of the original crater floor. And if you look at this area, so it's about 500 meters above this area. So we have some kind of a higher level, including bright material, above 500 meters of the highest point we have in this area. So I think that's an interesting part. We don't know how deep this material is going, but we have in this area something which is coming up or showing the bright material even higher than we have it in the central pit. Okay, if we look at the tectonics which is going through the impact crater, and I focused on the tectonics which is going through the plains material, we clearly see that there are tectonic features here, there are tectonic features which are surrounding the central pit, and there are a number of tectonic features going into this area and focusing in this area. And if you look at the height differences, so the tectonic is going from minus 200 meters to about plus to 1,500 meters. And I showed this before. We have this kind of radial cracks in this area, and the radial cracks are going into the mass wasting material, and they are also going into the plains material. So that basically means they have to be younger than the mass wasting, and they also have to be younger than the plain deposits. That's another view of this area, and you really can see there is some kind of a center here which show this tectonic features, and the tectonic features are obviously extension features. And if we go a little bit closer, then we really can see that this extension cracks are about 20 to 70 meters deep. And even if we go a little bit closer, we can see that something happened here. So this feature crosses this impact crater. So at least this feature is younger than this impact crater. We also have here some kind of a crossing of an impact crater. And even much more interesting is this feature. That's a dome which is 200 to 300 meters high. And if you look at this dome, so you really can see that there are a number of tectonic cracks which are covered by the dome, and other cracks are really cutting the dome. So there are some kind of a relative age difference in this area, and we really see that the dome overlays some cracks. And if you look at this dome, then we really see it's 350 meters higher than the cracks it covers. And it also we see the depression, which is at the top of the dome. There's a little depression here, and this depression at least shows up in the topography, and is about 50 meters deep. Okay, in summary, so we have some kind of a broken crater floor, where one part is 500 meters deeper than the other part. Then we have an age difference. I hadn't shown this, but there are a number of papers out of this, and or in preparation, and it shows that within the margin, the plains material seems to be younger than the ejecta. Then we have flows which are in the order of 150 to 300 meters thick, and then we have this bright material of Cerealia faculae and Vinalia faculae at different topographic levels, and we have the tectonic cracks which really show that there is something going on within the plains material, which is in the center of the impact crater. And we also see that there are relative different tectonic and different geologic features which overlay each other. So there is some post-impact processes are even going on within this impact crater. And finally, I think if you take together the topographic differences of the crater floor, the central depressions, the flow features, the orientation and age of the tectonics, the indication of which indicate post-impact processes, then we basically have two possibilities, at least from a topographic point of view. So we have a long-lasting impact melt pool, which has some kind of chemical reactions, probably impact hydrothermal processes, or we have some kind of contact to the subsurface. I call it cryovolcanism, at least for the reason that there are other features on Titan, on Ceres, which really show some kind of updoming, like Ahuna Mons. And it's obviously we have an impact crater, and the features we see, if it's cryovolcanism, it should be correlated with the impact. So there is one model, and I think Paul already explained this, that we have an impact. The impact produces a lot of melt, and processes, hydrothermal processes within this melt produced at least the central peaks and the material in the central peaks. And the second is we have some kind of an impact, and there is something beneath this area where we impacted, which has an whatever, more fluid material than the rest of the surrounding, and that's probably producing this plains material together with impact melt. So I'm pretty sure we cannot solve the problem or the question whether it's coming from beneath or it's impact melt due to geology or due to topography. We need the composition, and we need to understand the processes which produced this kind of composition in order to really understand the process within this area. Okay, thank you.
Thank you, Ralph. Questions?
Yeah, the asymmetry of the depth of the floor in the crater, couldn't they, I don't need it. Couldn't they point to an inclined impact?
You mean an impact on an inclined surface?
No, an impact. The impact is oblique.
Yes and no. It's hard to say. So there are the two possibilities. That can be an inclined impact, or it can be an impact on a slope, on a topographic slope. But usually we have an impact of about which produces an impact, a crater of about 100 kilometers diameter. So that's probably, if this impact is really really oblique, then we really should see it, because it should have an elliptical form. On the other hand, if it's going on a slope, we don't have slopes which are so high, the impact will throw away the slope. So it's hard to say, but probably yes. But we don't have the real identification of an oblique impact. It's not oblique by 10, 20 degrees. Maybe it's, is it oblique?
As long as the crater is circular, it's higher than. As long as the crater is circular, I guess the incident or the impact angle, so with the surface, is I guess steeper than 30 degrees. So when you get shallower than that, then you start to form elliptical craters.
Okay, summarizing, there is no real evidence for an oblique impact.
Other questions?
Are there any signs that the cracks are still growing?
That the cracks are?
Still growing, increasing in length?
Not with the data we have. So there is no changes so far. And it's hard to say, because the only observation for the cracks needs the highest observation we have, and that's about the 30 meters vertical resolution, and we only have got this one time. So we don't know whether there is any changes. And now we are in a higher orbit again, but that doesn't resolve the cracks, so we don't know. So, but it would be nice in order to understand what's going on.
Are there additional questions? Okay.